QED. So you did get your problem set on yesterday, and we finalized the description of the Feynman rules, the case scattering, so you should be able to know how to do that in principle. Now we're going to get slightly deeper into the basics. But before I start, any questions about last week's lecture? This week.
אני יכול לשאול כזאת אינטואיציה, אני יכול להסתכל על המושג הזה קרוס סקשן כהסתברות שחלקיק מסוים מפוזר עבור יחידת שטח קטנה?
לא, זה לא יחידת שטח. קרוס סקשן זה גודל שיש לו יחידת שטח, שהוא גודל בעל יחידות של שטח. כן? אינטואיטיבית, אתה יודע, בצורה הכי קלאסית, הכי טיפשית, תחשוב על שולחן פיליון, כן? מה הסיכוי שלך לפגוע במשהו? תחשוב על מולקולות קלאסיות שממלאות גז, ממלאות איזשהו חלל, עכשיו אתה שולח לפה איזשהו מולקולה אחרת, נניח אלקטרון לטובת העניין, אתה שואל, אוקיי, מה הסיכוי של אלקטרון הזה?
אסף, לא שומעים כלום.
לא שומעים כלום? למה לא שומעים כלום?
הבעיה אצלי, סליחה.
נפתור אותה. אינטואיטיבית, אתה יודע, מה הסיכוי שהאלקטרון נניח יפגע פה באחד מהאטומים פה? אם האטומים הם גדולים, זה סיכוי יותר גדול. זה הסיכוי. שאלות? QED, אנחנו, לא, את כל הקרביים של ה-QED, אבל זה מספיק שאתן לכם קצת. אנחנו נדבר על פוטונים, משוואות מקסוול, קליין גורדה ופרופ. מקסוול.
נשמע טוב.
מקסוול זה קומיישן קפה. פוטונס, קליין גורדון. פרופ. equations. טוב. QED זה quantum electrodynamics. אלקטרודינמיקה, quantum.
יש ספרים טובים לתחום הזה? כאילו...
QED?
כן.
It's the end of quantum field theory.
אוקיי, אז...
You learn quantum field theory and then you given the example, quantum electrodynamics. Okay? It's what I do in the end of the course in quantum field theory, then we go into QED.
עשינו טאנלינג לסוף...
עשינו טאנלינג, כן. קליין גורדון, אגב, זה כמעט קלאסי. זה כמעט קלאסי. קליין גורדון מוביל לדיראק. יש דיראק. טוב, QED, טוב, קלאסיקל. Okay, we make a discrimination between fields and particles. Okay. Classically, right, you have two electric charges. How do they interact? Fields, right? By fields. You have an electric field, you have a magnetic field, right? A charged particle can produce an electric field. If it's moving, it produces a magnetic field, right? And thereby affects the other charged particles around them. Okay, so classical E&M. By the way, you all took classes in E&M, right? Did you all see Maxwell's equation? Is there anybody who did not see Maxwell's equation?
ראינו. בשנה ראינו.
ובשנה ב'? לא ראית? מה?
לא, בשנה וגם ראינו.
הכל בסדר. So classical E&M, force between charges charges originates from electric and magnetic fields. מה קורה בקוואנטום פיזיקס? Quantum physics. Not quantum mechanics, quantum physics. What happens? What do we do with the fields? Quantize. Not quantize, but quantize. We quantize the fields, right? The fields become quantum. What does it mean? They become particles. Right? Which particle do the electric and magnetic fields become? Photon. Surprise, surprise. Yeah.
Electron also can count as
Electron is a particle. It has a field.
But for
it's an electron
example,
field.
photons can
The electric field and magnetic field, when they're quantized, they turn into, they get some particle-like quantities, and the particles are photons.
photons can exchange electrons between them.
In a way, yes.
So that is interaction.
Wait, you're jumping. Slowly. Quantum fields, quantum physics fields are quantized. And get properties of particles. And get properties of particles which are photons or electromagnetic fields. Which means that if you believe what I just said, which is what people teach you here, that means that when there is an interaction between charged particles, photons must participate in that. Right? Because classically, the interaction is mediated by electric field and magnetic field. Quantum mechanically or quantum physically, electric and magnetic fields becomes photons. That means that photons participate in the interaction between charged particles. So if you take these two together, photons participate in interactions between particles, charged particles. Now we basically draw Feynman diagrams, right? We said the interaction between charged particles are mediated by exchange of photons, right? Right. If we look at classical systems, we can still think of it as having mediated by photons, but there will be many of them, and they will have low energy. So they will act like classical fields. But when we go to quantum mechanics, then we start having discretized photons, which we see like in what do you call it? Photoelectric effect. And then you're seeing the discrete nature of photons are being seen when we talk about quantum mechanics. Okay, now what we need to do is to have a quantum mechanical description of a photon. Before I go and give you a quantum mechanical description of a photon, we need to go one step back and look at Maxwell's equation. So, description of a photon. Right. Before we do that, we need to start by Maxwell's equations. Or one is called covariant form of Maxwell's equations. Even before we start with that, we need to introduce units. E&M is notoriously known for having many different units. Right. So, what is the electric field of a stationary point charge? aka Gauss law. A. Answer the question.
Q over R squared.
Thank you. E. It's a vector, right? Is equal to what?
R Q.
K. Q over R squared in the radial direction.
And K is 1.
What the R? What is K?
1.
That depends on the units. Right? Now let's see. SI, what is K? SI is MKS, MKS.
8 or 9 point something.
What is K? Oh, come on. You said you did take a course in electromagnetism.
Oh, well, epsilon is, okay.
CGS?
1.
Yeah. Heaviside Lorentz? Heaviside. Heaviside Lorentz?
1 over C. No.
1 over 4 pi. Right? In Heaviside Lorentz, we have epsilon 0, right, is 1. And since epsilon 0, mu 0 is 1 over c squared, right, we have c equal to 1. Right? So, what does that affect? It affects what is a unit charge, right? What's the relation between unit charges? CGS is also called Gaussian, right? Gaussian. The reason why I write it is because if I say Gaussian units, then you know what that means, right? I'm not telling any news to anybody, right? You all knew that, but you somehow forgot. I'm just reminding you. Right, so what's the relation between the charges? So the charge in the Heaviside Lorentz. Heaviside Lorentz. How is that related to the charge in the Gaussian units? Right, which is 1 over square root of epsilon 0 q si. And similarly for the electric field, the electric fields in the Heaviside Lorentz units is 1 over square root of 4 pi. The electric field is measured in the Gaussian unit, which is square root of epsilon 0 of the electric field in the SI units. Yeah, I'm sure you've seen that, but you don't remember where or why.
We always work with MKS.
No, you never always work. Somebody showed it to you. Then they say,
Yeah,
okay,
yeah,
from here on we work in
I saw this, but
it's there. Forget about always. Because we're not going to work in MKS.
Yeah.
Okay. What about the fine structure constant?
1 over
Yeah, this is not changing.
It's universal.
That's a cute thing, right? So so alpha is Q in a Gaussian squared divided by h bar c, which is Q squared Heaviside Lorentz divided by 4 pi and over h bar c, which is Q squared Si divided by 4 pi epsilon 0, 1 over h bar c, 1 over 127 approximately. That's not changing. Yep. Right, yeah, okay. So I put a mark. So from here on we're going to use a Heaviside Lorentz. There is a good reason for that. Most particle physics textbooks would use Heaviside Lorentz, but there are exceptions, not all of them. Right? For example, Griffith is not using Heaviside Lorentz for reasons we should ask Griffith about. We prefer to use Gaussian units. So here's the exception. So most textbooks of this course would use Heaviside Lorentz. So will we. Yeah? Questions? None. Good. So the next thing I'm going to do is to write down the covariant form of Maxwell's equation. How many took the course in GR? 2, 3, 4. What? So the next will be familiar to you, partially familiar to you, and less familiar to those who did not take, but it doesn't matter. I'm still not going to lie. So Maxwell's equations. Okay, Heaviside Lorentz. Shoot, what are Maxwell's equations?
In a covariant form?
No, Maxwell's equation you know.
Gauss.
You're not supposed to know the covariant form yet.
דיווגנס של E שווה לרוב כלפי
That's Heaviside Lorentz.
של B.
Heaviside Lorentz.
What of E equals negative derivative of P with respect to T?
Right. Blah blah cross E. Right, plus 1 over C VTB equal to 0. But C is equal to 1. So nabla cross E plus VTB is equal to 0.
Nabla plus B equals to 0.
What?
Nabla plus B equals to 0.
How this? No.
Nabla dot P?
דבר כזה, לפים אותך פה. No magnetic monopoles. Yeah. No magnetic. Right? No magnetic monopoles. Right? This is Faraday's not me.
זה שאין מונופולים מגנטיים זו עובדה ניסיונית?
עובדה ניסיונית.
יכול
לא סתרו. למרות ניסיונות חוזרים בין אישים. אוקיי? זה גאוס.
יש סיכוי שבעתיד ימצאו או שלא? שכמעט בטוח שלא.
אני נביא. This is an experimental fact. No magnetic monopoles were ever discovered and people have searched for them. The last claim a few years ago, they said that they might have seen evidence for magnetic monopoles in the Big Bang. It turned out they did not extract the dust properly, cosmic dust. no evidence for magnetic monopoles today. If you discover one, the Nobel Prize is yours. You let me know. What we're left with?
Yeah, I'm very good.
Ampere, right? This is how we make electricity. Right? We should all take Ampere. How do we make electricity? Ampere's law. What of B? Yeah? Yeah.
J דואי לדתי.
One over C. C. C is equal to 1. So nabla cos B minus dTE is equal to J. Again, this and this is natural units. Now I know it's harsh to remember all these equations. Not really, but by the way, this is a standard question that people ask in if you want to apply for master standards. Simply remember.
Standard question for what?
Master. Okay, now we want to make a more compact form of writing. So we want to write them in a compact form. Why? Because we like it. Now, in order to do that, I'm going to make a short detour into the realm of relativity. So remember, when we started this course, we introduced the vector. Right, the vector. We had several vectors. There was a position, there was a momentum or energy momentum, right? There was acceleration, there was velocity. And I did not exactly specify what is a vector. Just say it's there, and nobody asked me questions about it. And I'm not going to give you the full theory behind it, or that you have to go to GR. But I'll just give you the basic idea. So the correct description of a vector, or to be more precise, called a contravariant vector, from a reason which will not be discussed here. It's called a contravariant vector. This is the exact technical term. Is an abstract object. A vector is an abstract object whose components transform as V alpha goes to V alpha prime, which is equal to lambda alpha prime beta, V beta. What is lambda alpha prime beta? What is that? This is a Lorentz transformation, right? So the components transform like that when the coordinate system transforms in the same way. X alpha goes to X alpha prime, which is lambda alpha prime beta, X beta. So, we have two coordinate systems, namely there are two observers. One and the second. They have two different coordinates, namely one is moving with respect to the other at a constant velocity. So one has coordinate system with an alpha, one has coordinate system with an alpha prime. The transform from one location to another, we make a Lorentz transformation. This is a 4x4 matrix. I defined a vector as any abstract entity that whose components transform in the same way as the coordinates. Okay? Not everything is a vector. What we saw, like velocity, is a vector. Right? Energy momentum vector is a vector. Okay? This is a vector. The vector itself, what happens to the vector itself when we make the transformation as opposed to the components? What happens to the vector? Nothing. The components is the way we describe the vector. This is a vector. Put an arrow. Now I make a transformation to the coordinates, right? This is the components of the vector v. So this will be vx, and this is it, vy. So I write down the vector v, vx, vy. Right? Now I'm transforming the coordinate system. So rotating. This is O prime. What happens to the component of the vector?
They change.
They change, right? Now it's Vx prime, Vy prime. Vx prime, Vy prime. What happened to the vector?
Nothing.
Nothing. It's the same abstract entity that it was before. It's just that the description of the vector changed when we changed the coordinates. Okay? Now, so the change is done in such a way that the vector is an abstract entity, nothing happened to it. Okay? So, we can think of a vector, and this is the next jump in abstractization of what I'm doing here. We can think of a vector as a linear map from the coordinates to R. Right? So, and I'll write it down. We can think of a vector as a linear map from the 4 coordinates to R. Those who took the course in GR know exactly what I'm talking about. Those who do not, sounds a little bit strange, but this is exactly what a vector is. A linear map between the coordinates and R. Okay? Now we can, why am I doing that? So that I can generalize that. To what? To tensor. Right, so what is a tensor?
Multilinear map.
It's a linear map, right, between two, well, it's called covariant vectors. I did not put this Spanish, yeah, so the coordinates, I said that from the 4 coordinates, they define what's called a covector. Or covariant vector. So similarly, you can think of a 2-0 tensor is a linear map between two covectors and R. And the 0-2 tensor is a linear map between two vectors in R. Is a linear map between two vectors and R. Now we have seen one 0-2 tensor, which is the, we have seen it in this class.
Eta?
Metric tensor, that's right. So that's why it's called the metric tensor. Example of a 0-2 tensor, eta mu nu. And if you note that, the two indices are subscripts. 0 up, 2 down. That's a 0-2 tensor. And the vector, right, it's a 1-0 tensor, so that's why I put it with one upper index. Always. Okay.
אפשר שאלה?
כן.
What is the difference between a covariant, a co-vector, and a vector?
They live in dual spaces. Basically, they do not live in the same space. You cannot add them. Right? One can act on the other, like you have. You can think of it as a row vector and column vectors, if you prefer.
Okay.
Okay? Or Dirac bras and Dirac cats. Okay? You know what is a Dirac bracket?
Sort of.
Sort of. That's taking the course in quantum mechanics. Okay. So after very insufficient definition, which is difficult for me to expect that you actually understand all the hidden logic behind it, but I did give you the exact definitions right now. So now I'm going to define a new tensor. So we combine the electric and magnetic fields into a 2-0 tensor, which is known as the electromagnetic tensor. It has several names. So it's either electromagnetic tensor, it's also known as the Faraday tensor, it's also called the field strength tensor. These are all three names of the same thing. Since it's a 2-0 tensor, then it has two upper indices. It's called F for Faraday. F mu nu is defined as, oh again, it's a bit tricky because of the sign convention. It's kind of annoying. So she has 0 on the diagonal, and then there will be a minus E1, minus E2, minus E3, plus E1, plus E2, plus E3. And here it's a bit more tricky, it's a minus B3, B2 with a plus, and a minus B1. Here it's a plus B1, minus B2, and B3 with a plus. That's the definition of a Faraday tensor. So I took the three components of the electric field, the three components of the magnetic field, and I just put them in one tensor, which is written as a matrix. This tensor can operate or can work on two covectors and give me some number R. That is the mathematical definition. Now, of course, E1 is AX, E2 is EY, and E3 is EZ. Right, just to make sure that nobody misses anything important here. Right, about the sign. For some reason, some strange reason, there seems to be no exact convention of the signs here. I am following the same sign as Jackson. You know the book by Jackson?
Yes.
Yeah. Do you know the book by Jackson?
The classic book for
Yeah.
very
Okay, it's the same in Wikipedia. You know that, right? This is the convention. This is the sign convention of Wikipedia. But some of the classical E&M textbooks use the opposite sign. So F mu nu that they define is with a minus sign. So here it's a plus, and there is a minus here, and everything is first order. So pay attention to that. Again, Griffiths and some of the textbooks in astrophysics use the opposite sign. Why? I'm not sure. It seems that the literature never converged into what should be the right sign. Always. This also confuses me, so that's more tricky. So yes, so just get used to it. If you go to Wikipedia and you write Faraday tensor, that's what you're going to see. Okay? Good. Now, we are 80% the way of writing down Maxwell's equations, which are still written here in a much compact form. For completing, I'm going to introduce to you a new 4-vector. So let's call it a 4-current 4-vector. It's called a 4-current 4-vector, which is a 4-vector. I write this as a mu, right? It's a J mu, and because it's new, I'm just retaining the C. It goes C rho, and then J, right? Jx and Yjz. This is the same J, and this is the same rho. This here. Yeah? Nothing that should alarm you. Now, we have 4 of Maxwell's equations, right? 2 of them are homogeneous, so there is a 0. 2 of them are non-homogeneous. So now I can write down these 2 non-homogeneous Maxwell's equations. How? Very compact form. J mu. J mu. Now I can write down the 2 non-homogeneous Maxwell's equations. How? Very compact. V mu F mu nu equal J mu. This is equal to that and that together. You see that? No? I've seen that before. Yeah. Right. So if I put nu equal to 0, right? What is F nu? Okay, mu equal to 0. F 0, 0 is 0. I don't care. Mu equal to 1. D mu F 1, 0. What is that?
D1.
D mu is D1 is dx. F mu 0. F1 0.
E1.
E1. Ex. But we have to sum, right? There is a summation here over mu. right? We have the same index as a superscript and a subscript. So there is a summation here over mu, right? Remember that? So dx ex plus dy ey plus dz ez is equal to j, you said nu is 0. What is j0?
0.
Oh. What is that? dx ex plus dy ey plus dz dz? What? Nabla dot e, right? dx is d over dx. dx over dx plus dy over dy plus dz over dz. This is nabla dot e is equal to rho. Promise me. So this is both of these together. What about the homogeneous Maxwell equations? Still have two, so this is two Maxwells. Now we get
You need the brackets.
yeah, but I can do many things. What I'm going to take the easy way,
Brackets.
which I'm going to introduce another 4-vector, right? To make life easier or harder for you, that depends on the point of view. Right. Now, did you see the electromagnetic potentials? Ah, okay, good. Right. So, nabla dot b equal to 0. That means we can always write b as a curl of a vector potential. Right? So we can write down b equal to curl of a. And A is a vector potential, right? Why? Because the gradient of the curl is always 0. So we can put in A whatever we want. It still give us a 0. Now we can put that in Faraday's law. It's here. Which will have nabla cross B is nabla cross A, so in B, nabla cross and dp are exchangeable. So we'll have nabla cross E plus 1 over C dta is equal to 0. We'll just copy it from here. I even turn the C. Well, let's change the order of the derivative, the time derivative and the special derivative. Now we all know that the curl of a gradient is 0. So since nabla cross nabla u is equal to 0, curl of a gradient is 0. Which means that we can write whatever is here in terms of nabla dot u, which u is a what? Some potential, a scalar potential. So we can write down, instead of u, I'm going to just write a phi. So I'm taking these two and write E plus 1 over C dta is equal gradient of phi. Or minus gradient. And phi is called the scalar potential. Guys, you've seen this in your game now? Yeah. Who did not see that? One? Why? Did you learn it yet?
I learned it.
Also, yeah.
I don't remember this.
זה V.
זה וי פשוט. במקום
וי?
פאי ווי.
V של שנות.
לא זוכר.
Blackout. be very surprised if nobody showed you that in how do you call it? Fields?
זה
האינטגרל
בסדר
שלי.
בזה.
איזה שנה זה?
בלי כמה.
חלקי.
לא, על חלקם לא בסדר עדיין.
לא אמיתי.
Okay, look, all the math is here. The gradient, the curl of a gradient of a scalar function is 0. Is that you know? You learned it somewhere? So I can simply put instead of that, if this is 0, I can put it here. Don't need anything more than that. Right? Now the thing that did not, so far,
Why the negative sign though?
just because. Right? Now the thing that did not show you in what do you call it? Sadot? Fields. So I can introduce now a new 4 vector, which is called the 4 vector potential. So 4 vector potential. You can write it down as A mu, which will be a what? P and A. Exactly. But it's cool, right? It's very compact, right? And it's all consistent with relativity.
Very easily.
למה לחבר אותם?
למה לחבר אותם? נו, באמת, למה?
With that you can write very easily.
What am I trying to do?
טוב, הכל בשורה אחת.
Yeah, exactly. Trying to compactify all these Maxwell's equations. So I got one.
You can write if that very easily in the tensor, right?
The what?
The electric field tensor, Faraday tensor.
Yeah. Well, this is the Maxwell's equation.
Yeah, you need the.
So we have the two homogeneous Maxwell's equations, which are essentially this and this, which is this, right? This and this. This is the homogeneous Maxwell's equations, right? As f mu nu is d mu I nu minus d nu I nu. Up to some minus sign that I might have forgotten, no, but this is the correct one. Check in Wikipedia. They have a different thing. That's it. Yeah.
Supposed to have a different sign.
What? No. This is B. So, I don't know. B3, right? B3 would be F12, right? F12 is a minus B3, so it's F21 minus F12, right? This is B3. Right? So D2A1 minus D1A2 is exactly the root. If you put 1, 0 there, then you get DTA and you get that. Yeah, play with that at home and you can see it. So yeah, so instead of using these equations, I'm using these equations. One, because it confuses you, and the more important thing is because this I can quantize. Which I will, shortly. And just as a note, as a comment, okay, before we quantize, there are a few more steps that we need to take. Questions about that? Yes.
How do we know that those 4 vectors you defined really are 4 vectors?
How do we know what?
That they are 4 vectors and not some symbols that don't transform well.
Here you trust me, they will transform well. Okay, and how do you make 4 vectors?
No, how can you prove it? That they transform well.
In second course.
How do they transform it?
In
How do you
second
prove it?
course
No. Maxwell's equations are consistent with relativity. Did that anybody show you that?
No, no,
In fact, if you think of it, Lorentz came before Einstein. Right? Einstein used Lorentz transformations in special relativity. And Lorentz got this transformation because he wanted to see how electric and magnetic fields transform from one reference frame to the other. Did they show you that? They should be in one of the advanced E&M courses. If I'm giving you an electric field and a magnetic field, right? So let's say I put a magnet here. I can calculate what is the magnetic field. And then I can ask the question, what would be the electric and magnetic field that will be seen by an observer that is moving relative to that magnet? So how electric and magnetic fields undergo transformations. Did anybody show you that?
זה ירד בחומר בגלל השליטה.
רק? מה?
היה שליטה.
השליטה. I see, okay. Awesome. Okay. They go like that in Lorentz transformation. Okay, that's it works, right? That's how Lorentz actually. That was Lorentz's motivation to put his transformation in the first place. Okay. How do I prove to you this is a 4-vector? Here you simply trust me. This is a 4-vector. Because you can simply write down this equation and you get back what you give. Yes, that's the easiest answer I can give.
Can I ask a question?
Yeah, you can.
Where the second Maxwell equation get into the final equations?
This one, the homogeneous one, it's here.
Yes. Okay.
Just put one of them mu and u equal to 0 and find for yourself and solve it. Okay? It's quite a cool game to play, so just play in your free time.
There is a much final equation like that collage this.
These two?
Do the yes.
No. Basa.
More simple than that?
No.
They're actually
no, because two are homogeneous. These are homogeneous ones, and two are non-homogeneous. There is a source. This is a source term, right? This current is a source, right? For current, right? It's you have a charge and you have a current, right? Yeah. So charge is a source of electric field, and current is a source of magnetic field. Yeah, that's what we have.
UGL, you showed the one of the buckets, so it will be shorter.
It's not short. It's the same.
Yeah,
it's the same level 8. You can put it in a different form. I don't have any reason to do it right now. There is a reason why I do all that, right? Remember we started QED, right? We do need to quantize all that. Everything still is classical, right? We will quantize it. I'm not going to quantize this. I'm going to quantize this. But one step at a time. Okay. Now, before that. Yeah, I can use that definition here. Right, I could write down this for a question. Basically, maybe this answers your question. I can plug it in here. It's not going to give me any new information, but now I can erase the Maxwell equation. Right? Oh, now you got that. They're already written in the board, so I don't need them twice. Now I can plug it in here. This will get in here. It stops getting any words. So we have d mu, right? So then I have d mu a mu minus. I can switch the order. D mu d mu mu is equal to j mu. Now we have an operator really that looks like d mu, which is 1 over c squared dt squared minus nobla squared. Laplacian. Guys. Okay. I'm playing, right? But if you've never seen that, this can be extremely confusing. So I don't take it as if like I think it's very easy. After I did it 10 years, it gets very easy for me, right? But if you've seen it for the first time, no, it's not very easy. You have to practice it. You have to read it, right? And the fact that you're sitting here and I'm just throwing out all those symbols on the board does not mean that I think it's easy. Okay, so no, it's not easy, and you have to practice it. So make sure that you practice it, because we don't have time to practice it in class. You have to practice it at home. Go to textbooks. It's a standard thing in any of these. It's not basic, right? It's advanced textbooks, but it's doable. If you need some help, then come and ask them. This is, some of you know, what's the symbol for that? This is called D'Alembert. It's a square. This is called D'Alembert. Which is the 4D Minkowski space generalization of the Laplacian. It's really Laplacian here. Okay, so this is called 4D D'Alembert. For your knowledge. So we can basically write that as D'Alembertian of I nu minus d mu I nu is equal to J nu. And we simply, I don't think it gives us more information. It's just a way of writing down the Maxwell's equations. This is the non-homogeneous Maxwell's equations using the 4-vector potential. Right, so a few comments. So there is some sort of switch of focus, let's say, right? When you learn electromagnetism, the important things were the fields. Talked about electric fields, magnetic fields. You did, I believe, right? You did study these potentials, right? The vector potential and the scalar potential, but they were derived from the fields, right? They were not by themselves. What happened? Something like that. In quantum physics, the basic entity now is actually the potentials, not the fields. The fields are derived from the potentials. Where you can see that, did you hear about the Bohm-Aharonov effect? Quantum mechanical effect, very cool. What? תראה זה? לא בטח לא יודעים את זה בתואר שלך. מי לימד אותך? Bohm-Aharonov, מי לימד אותך?
לב חייקוביץ'.
אוקיי, חמוד.
ממש? פעם ראשונה שעשית את הקורס הזה ככה.
לא, בסדר, אחלה. כמו שזה יותר דויד Bohm-Aharonov, אבל אהרונוב הוא מתל אביב, אז הוא משלנו. Bohm-Aharonov, or Aharonov-Bohm, you see directly just from the potentials. You cannot see it from the field at all. It's a quantum mechanical effect. Right, and the other thing is that the homogeneous Maxwell's equations are automatic. Once you plug in the vector potentials, everything is just automatic. You don't need to do anything. Okay. The next thing we need to do before quantizing is another thing which I believe. Okay, questions. Questions. Yeah. Maxwell. These are Maxwell's equations. Yeah. Right.
כאילו ההצדקה עליהם זה מהשכתוב של משוואות מקסוול בצורה יותר נוחה.
These are Maxwell's equations written not in terms of the fields E and B, but in terms of the 4-vector potential and the 4-vector current and the Faraday tensor. But in terms of the physics, they contain exactly the same physics as the Maxwell's equations. The language is different. Why? Because with that language, I can easily, and I know how to make transformation from one observer to another. This is fully consistent with what happened in special relativity. If I write down electric field and magnetic field, and now I start to ask you, how are the fields transformed under Lorentz transformation? You'll get very confused. It's not easy. If I ask you how the 4-vector potential transform under Lorentz transformation, you know immediately the answer because it was written here on the board half an hour ago. The same goes for the 4 current. Nearly the same goes for the Faraday tensor. So this can easily be generalized to any observer moving in any frame. Okay, and you don't need to work hard at all. Don't need to work at all. Okay, so after you get used to it, it's really getting much simpler. The next thing is also something which you're supposed to see, and I believe that many of you see. Gauge transformation. Who saw gauge transformations? It's all part of a classical ENM, or it's called the electromagnetic fields, or whatever you call it. Classical ENM. Who saw that? Gauge transformation? Or you also don't remember that? Oh, it seems like you did not see it. Gauge transformation. No? Yes. Yes, no, maybe?
I saw.
It's okay, I'm showing it to you now. I didn't believe it's the first time that I'm not sure. This is supposedly standard in electromagnetic fields. Okay. Now, do we measure A and phi? What do we measure? What do we measure?
Fields.
Fields. We measure electric field and we measure magnetic field. Yes. Right? We put charges, we measure fields. We do not measure these. These are computational tools. Okay? So this is a bit tricky because, I don't know, for me as a student, I was a little bit confused by it. So I assumed that if I was confused, everybody would. That's my pre-assumption. Right? So we don't make this. So the fact is that we do not see these potentials. These are computational tools that we use from which we derive the fields. Okay? Using the Faraday tensor and right, the field is a derivative of the potential. Right, which is in here. So the fact is that we don't know what are the potentials, and they are not fully determined by the fields. There is still a degree of freedom, right? Degree of freedom, which is there. So phi and A, phi and A vector. So this is the vector potential and the scalar potential. Are not uniquely determined by the fields. This is what we measure. We measure. So for given fields, there can be more than one set of vector potential and scalar potential that are consistent with these equations. That means that we can add since the fields are derived from the potential, right? We take the potential and take the derivative, right? Then we can add to the potential an arbitrary scalar function, right? So if we are free to add to the potential a gradient of arbitrary scalar function lambda without affecting the resulting field. Namely, if I have, instead of a mu, I write down a prime mu, it's a prime. I'm not making any Lorentz transformation. I'm just looking at a different vector potential, which is equal to a mu plus b mu lambda. Lambda is any function of space and time, right? This is not going to change the electric or magnetic fields. Will not change the electric or magnetic field, since b mu a prime mu, a prime mu, sorry, prime mu minus b mu a prime mu is equal to d mu a nu minus d mu a nu. This is just a scalar function. Okay? So mathematically, I don't really know what is the value of a nu. It's determined, but up to an addition of a gradient of a scalar potential, a scalar function, sorry, which will not affect the resulting fields, which is the important term. Okay, with me? Now this is transformation from a mu to a prime mu as a name. This is called this is called a gauge transformation. What is a gauge, by the way?
You use it to measure a field?
Gauge is a scale.
Oh.
Just a scale. Right? Because it changes the scale basically of the instrument in which we measure this vector potential. Now the guy who found that is a guy that we're going to encounter his name a lot in this course. It's called Hermann Weyl. Should I write his name properly?
It's also the one with the Weyl tensor?
Yes. Yes. Hermann Weyl. I'm going to show you that he nearly reinvented half of the physics, by the way, by this gauge transformation. People don't realize what, if you know what he did, then you realize what he was doing. But it's not really taught. He's one of the geniuses that reinvented half the physics, basically. So this is called a gauge transformation. Okay? Now the fact that the fields are not changed, namely they are symmetric under gauge transformation, is called gauge symmetry or gauge invariance. The fact that the fields do not change under gauge transformation is called gauge symmetry or gauge invariance. Gauge invariance. Okay. Now, given that we have this gauge invariance or gauge symmetry, and the fact that again we can describe Maxwell's equations, namely the electric and magnetic fields, by these potentials. So it's a great computational tool, but it's not determined precisely, but there is a freedom called the gauge freedom. Right? We basically have two options that we can do. Right? So the two options we have is either one to say, okay, we'll just stick to A and live with that. We know that it's not uniquely determined. There could be some other physicists that use a different A, but that's fine. We just live with that. So we can do either. We can
add another assumption.
Either, yes. One. Continue use a mu, knowing it is not fully defined or completely defined. It's fully, but it's not completely defined, uniquely. This is called the spurious degree of freedom. Or we can put an extra constraint. Or impose an extra constraint and work only with the physical degree of freedom. What's the problem with that? Take a risk that it's not going to be Lorentz invariant, everything we do. So we have to be careful what we're doing here.
But if you will add another assumption, you before assume, כבר הנחת לפני כן שזה אינווריאנטי על לורנץ, לא?
Everything I wrote here is Lorentz invariant. But if I put an extra degree of freedom, if I put an extra constraint, I have to be very careful in how I put the constraint, because it is not necessarily going to be a Lorentz invariant.
נכון, אבל...
That's what I'm saying.
אוקיי.
That's all I'm saying.
אתה יכול למצוא תנאי על הלמדה,
אז עם כל מיני תנאים, אבל זה מאוד זהיר במה שאני עושה. Now, the question is what we're going to do depends on what we want to achieve, as usual. Right? Now, since we're interested in studying physical degrees of freedom, we're going to take this approach. Right, the second approach. I thought that you've seen the thing before, but if not, then see it now. So, we're going to the extra, so let's take the second approach. So, take this approach. And we choose lambda. Lambda such that, right, lambda is here. So we choose lambda such that d mu is equal to 0. This choice of lambda has a name. This is called Lorentz condition. What? הזכרתם? Tom קפץ. So you confirm that you have seen that?
Me, but I don't think I will.
Well, at least you can see that I'm not cheating.
Yeah, you're
I'm not cheating, right? Right, who saw that? Lorentz condition? Some did, but most of you did not see it. This is called the Lorentz condition. Okay. Now, the homogeneous Maxwell's equation, which I've already erased. Let me write them here again. Right, so we have number A nu minus B nu A nu equal J nu. Right? So in the Lorentz condition, what do we get? What do we get of this Maxwell's equations?
A nu equals J nu? No.
The Lagrangian of A nu is equal to. Right?
Who invented this symbol?
Which is pretty cool. Now in QED, that is going to be the wave function of the photon. Bear that in mind, but I don't know if we'll have too much time to do it today. If we have a vacuum, so okay, if I already said it. So in QED, this is going to be the wave function of the photon. In vacuum, what do we have in vacuum? J nu is 0. So in vacuum, J nu is equal to 0. And what do we have here? This equation becomes the Lambertian of A nu is equal to 0. What is the Lambertian? What is the Lambertian? I wrote it. Right? So this is dt squared minus Laplacian squared. Right? So what equation do we have here? In vacuum?
Wave equation.
It's a wave equation. Which is what Maxwell's equation of a wave equation in vacuum. Did you see that? This is something we should have seen. We just proved it. Okay, so wave equation and the speed? C, 1. Right? Speed is 1, which is C. So in vacuum, which means that A nu satisfies the wave equation with speed of velocity 1, which means the wave with phase velocity equal to C. Yes.
You say in vacuum, but you probably eventually get in vacuum there are a lot of virtual particles, even charged virtual particles. Will they contribute to a J?
The answer is no, but the basic answer, everything we did in this class was completely classical. I did not quantize anything so far. I just took, what did I do? I took Maxwell's equations. In fact, I thought that most of it you have seen. That was mine. Foolish me. I thought that you have seen that in your classical course, one of these. So it's good if everything was classical. I did not quantize anything here. Right? This is what did I do? Took Maxwell's equations, and I just introduced to you the Faraday tensor. I introduced to you the 4 vectors, the 4 current vector and the 4 potential vector. I just wrote down Maxwell's equations in this form. And I told you that this form has several advantages over the classical way of Maxwell's equation that you're familiar with. One is that it is automatically, you can transform it from one frame to another frame, completely self-consistent with everything we did in special relativity. It's completely automatic, the transformation is automatic, you don't need to think. The second thing which I told you, and I did not prove it yet, is that this is something which is going to be easy to quantize. Okay, so this is the reason, this is what the motivation for this. Then I spoke about gauge transformation, right? Telling you that I'm going to work with these potentials, and I mentioned the fact that these potentials are not uniquely determined by what we can measure, which are the fields. Okay? More questions? That's important. I thought we'd be much faster because I thought that you knew all that, but I took into the possibility that you did not. So I'm glad that we're doing that. Guys. I assume that many of you, those who did not study with me already in the course of GR, one of those, are not familiar with this notation. So this can be quite confusing at the beginning. After you get used to it, it gets very simple. Before you get used to it, it's very confusing. So go over it. I urge you to go over it slowly at home. I'll try to put my lecture notes as soon as I can. Some of you know I'm super busy, super busy. So that's why I put the decay part on the course webpage. This will be put on the course webpage as soon as I find time to complete it. Then it will be there, but don't even rely on that. Rely on the textbooks and go and make sure that you understand it. Again, it's standard in a way, but you know it's not basic. So this is not the course for it's not the first year. Okay? And when you get used to it, you say it's not that hard. Makes sense. Okay. More questions? Shall we start quantizing? Yes. Yes.
We have 5 minutes, so you can wait.
You can do it in 5 minutes. Take a talent from here to. Right. So that's okay. Let's just let's start with some basics, and then we'll really do the quantization next week. Right. The problem is not the 5 minutes. The problem is that we only have 9 weeks or 10 weeks in this semester. That is the real problem. Now, 1 week I will not be here. For 1 week I have to travel, which means that I will circulate in one of the next 2 weeks. I will circulate a timesheet for everybody to fill in when we can make a lecture compensating for that. In fact, I think I'm only have to fill one because I will be away. There is one day which is supposed to be the municipal elections, right? I think it's a Tuesday. I don't know if it's a holiday or not, but it doesn't matter. We'll just fill in the form and we'll find out time to compensate for the lost lectures. I'm not going to give you extra unless you really ask me to. Okay? That's because I'm not allowed to. But I guess you want to learn about the Higgs mechanism, which is the last one. I cannot talk to you about the Higgs mechanism before talking about QED.
מה אתה אומר למה שירד בקורס?
מה? יש כל מיני דברים שירדו בקורס. חלק מהתרגילים שלכם ירדו בקורס. Nuclear physics went down. I have to see how much time I'll have if we go over the full week interaction, because there are some tricky points there. So I might skip. And there are some parts, by the way, you can see in my lecture notes, there are some parts which we did not cover. These are parts that I think are not needed. Okay, quantum. So let's start with the quantum interpretation. So quantum interpretation. So basically everything we did was up to now fully classical. How do you know? There was no H bar. There was no H bar, it's classical.
Yeah,
you see H bar, it's 1.
Yeah,
the H bar is 1, so you cannot see it, right? But there is no H bar in Maxwell's
equation. You never know.
No, there is no H bar in Maxwell's equation. Right? In Maxwell's equation, still, there was no H bar. Right, but as we all know, photons are quantum entities, so we cannot just ignore it. So now, right, we have to start thinking of A. We said A mu really obeys a wave function, right? We just ended with A mu being a wave function. So we now think of A as, we interpret A mu as a wave function representing a photon. That is our interpretation now, right? So far it was a classical vector potential. So A mu, we interpret A mu as a wave function of a quantum photon. So how do we quantize a classical system? How do we quantize a classical system? Come on, you know.
Convert to operators.
Right, what do you convert to operate?
Derivatives.
What do you convert?
I
What?
said derivatives, but I'm not sure.
You
What
need to set
classical
a
entities?
mu to be an
Momentum and
operator.
energy.
Momentum and energy, thank you, right. So what is energy? Energy
Newtonian.
is what?
I mean,
IH bar d over dt.
yes.
dt. And the momentum?
Minus
IH bar nothing, right? These are operators operating on. They're operating, they must operate on something. Operating on what?
The wave.
On the wave function, right? So they operate, that acts, convert P and P to operators acting on a wave function. Wave function, I'll just put it psi. So, quickest way of deriving, not really, Schrödinger's equation is absolutely. How do you derive Schrödinger's equation to you?
Equals to
Equal classical,
P
right?
squared divided by 2m.
P squared over
plus
2m plus v. Right, you have seen it, right?
Yes. Even though flexure.
Even of that's the quickest way, right? So that will turn out into just applying this prescription, we automatically get that minus h bar squared over 2m and lambda squared plus v psi equal h bar dt. And voila, we end up with Schrödinger's equation. So if you think of it like that, what does it mean? So we think of Schrödinger's equation as what?
Wave.
Energy conservation equation. It's a kinematic relation between the energy. Right. That is a kinematic relation between the energy components of a non-relativistic vector. Non-relativistic particle. That's the problem. That's why we cannot use it. This particle cannot be non-relativistic. So this has a total particle energy equal to kinetic plus potential. Oh, okay. What happens if we do the same for the photon? Let's try to write the analog for photon. It's not hard.
E equals A.
Yeah. So
Times
photon.
I don't care about C.
Good. What about M?
M photon?
Very
no.
good. There's no M. Right. So for photons. Right. So for photons we have E squared minus P squared is equal to 0. Right. Or if you want to write it in the covariant form, this will be a P mu equal to 0. Right. Now we can write down the energy and momentum in the covariant notation. Right. So we can write down P mu. What is P mu? Is E and P. Right. So this transforms in the quantum mechanical transcription to I dt and minus nabla.
You need to quantize time or something like that, right?
Not quite, because quantizing the energy and the momentum.
Okay.
dt and minus
Yeah.
that's it, okay. which, if you, this is I, d over dx0, d over dxi, or I d mu. So it means that P mu is E and minus B, which will go into I dt and nabla, which is I d mu. So when we take the photon and promote the photon momentum into an operator, so promote the photon momentum into an operator, what do we get? P mu give us a what? Minus d mu, which is, you said it. What is that?
This is the Albertian.
Yeah, this is a minus the Albertian.
Okay.
Right? So, we just had 10 minutes ago, right? What did we just have? I wrote down a wave equation for A mu, right? What was my wave equation for A mu?
The
Albertian of A mu was equal to 0. What do I do now? So we had the Albertian of A mu equal to 0. This was a wave equation for A mu.
I'm just applying the operator twice.
No. No. This was, when we wrote it down, this was a classical equation. When I say classical, it's supposed to quantum, right? It's classical,
yes.
Relativistic, right? It's a classical equation for the 4-vector potential A mu, which was written classically. But now, I take this equation for the photon, I turn it into a quantum mechanical by turning P into an operator, and I end up
on the wave function.
which means that what? If I look at the same equation as being a quantum mechanical equation, that means that A mu is the wave function of the photon. Right? So this is my interpretation, right? This is how I look at this equation. It's the same equation, I just view it now differently. Okay? So A mu in quantum mechanical interpretation, or just quantum interpretation,
It actually makes sense because
A mu becomes the wave function of the photon. And this classical equation is now interpreted as a quantum mechanical equation representing what? Conservation of energy and momentum. Right? This is the kinematics from a massless photon. Again, this is our interpretation. Right? This is how we look at A mu in this framework.
עכשיו אנחנו מקיים משוואת גלים.
כן.
משוואת גלים.
משוואת גלים קלאסי. עכשיו אנחנו מדברים על quantum mechanics.
כן, לא, דיברת על משוואת גלים קלאסי.
What I'm doing, I'm taking the classical wave equation. Now I'm interpreting it. Now I'm giving a different interpretation to A mu, right? That's important because I don't think you've seen it. Right? You said, okay, a particle would be by some wave function psi. Now I'm saying this equation, when I look at it from a quantum mechanical point of view, then A mu, I can think of it as a quantum mechanical interpretation, a quantum mechanical equation, not a classical. If A mu, I interpret it as the wave function of a photon, because it fulfills this equation, which I know photons produce, and the quantum mechanical prescription of the transformation of the classical momentum into operators. Okay? Make sense?
Yeah.
Okay. Any questions? Now it's fine, because now we reach the point that when asked if there are no questions, people don't say anything. I do not believe that you understand everything. Before I do, yes.
It's been a long time since we learned,
Long time, yeah.
like with OFEC. Can you remind us?
What do you mean by long time? Like last year, was it?
No, it was like a year and a half ago. Yeah, it was a long time ago. So why do E and P get those operators?
Why do?
Yeah, why? Where do these operators come from for E and P in classical quantum
That's a
mechanics?
transition from classical to quantum. Why? That's not with OFEC. That's a basic course in quantum mechanics.
OFEC also did that.
I don't know what OFEC is doing. Why you interpret? That is the basic question in quantum mechanics. Why in quantum mechanics?
No, I get why we interpret.
This is a postulation, I guess. I don't have.
Why these specific operators though? Why I times H bar times the derivative with respect to T? And why these?
At a deep manner, it is associated with the conservation. Conservation of energy is associated with symmetry of time. Conservation of momentum is associated with symmetry of space. At a quantum mechanical level that you are familiar with, it will take me some time to think of it before I can give you a proper answer. Go to my webpage. I taught quantum mechanics once. And of course, it's there, so it's likely there is an explanation there somewhere. Yeah. More questions? Okay. Yeah, I think we reached the point that you need to start repeating the material, so make sure that everybody stays with me. And we don't lose more students on the way. Yeah.
את האופרטורים של האנרגיה באנטנה תיארנו מה שמופיע, מה שקורה לפונקציית גלים מהצורה של E בחזקת I kx מינוס אומגה t, אבל כאילו...
You're confusing things. I did not specify what is the wave function. The specific form of a wave function is true under certain conditions. The basic idea behind quantum mechanics is that you take some entities, such as quantities that classically represent measurable quantities of a system or of a particle, like energy or momentum, and they turn into operators. And the particle is not represented by a point, but represented by some wave function.
כן, אז את האופרטורים...
I did not say what is the wave function, and you can solve Schrodinger's equation and get a wave function under certain conditions.
התכוונתי שכאילו ההשראה להגדרת האופרטורים להיות מה שהם הייתה מהבוללות בפונקציית גל הבסיסית של E בחזקת I kx מינוס אומגה t, לראות איך האנטנה...
פונקציית גל בסיסית, the basic wave function you describe is for a free particle. There is no potential.
כן.
This is a specific condition, which what I'm doing is more general.
כן, יודע.
Okay. You say an answer to that? I think there is something deeper there, but I need to think. I don't want to just...
למה אבל עבור פוטון כאילו הגדרת האופרטורים של האנרגיה באנטנה לא, כאילו ההגדרה שלהם לא תשתנה, כאילו למה היא נשארת ככה?
למה שתשתנה? This is, for photons, right? E is equal to P, it's massless, right? E squared is equal to m squared plus P squared. Right. And m is 0. Photon is massless. If the photon had mass, it's a different story. It does not have mass, right? This is the... What I'm doing is more general. Okay. You say an answer to that? I think there is something deeper there, but I need to think. I don't want to just...
למה אבל עבור פוטון כאילו הגדרת האופרטורים של האנרגיה באנטנה לא, כאילו ההגדרה שלהם לא תשתנה, כאילו למה היא נשארת ככה?
This is for photons, right? We derived that in first or second part of the course, right? Special relativity, kinematics. This follows from the direct kinematics of special relativity. Okay? And it does not change when we go from the classical world to the quantum world. And that's it. So this is, go to the second lecture, I think we had a third lecture, something like this. Okay? More questions? Guys, review that. Okay? I'll make an effort to put my lecture notes as soon as possible, but it takes some time. Good luck. Have a nice weekend. Think of questions. I'm available to answer. So here,